Hello, my name is Natalia, and I will be present a first estimate of the displacement of Mono Ethylene Glycol in an oil pipeline using Computational Fluid Dynamics. In oil and gas production systems, when properties such as pH, temperature, pressure, and concentration of dissolved ions in the injected water are modified, the chemical equilibrium is disturbed, causing the precipitation of dissolved ions and the scale deposition. This is threat to flow assurance has been an issue addressed in the search for the effective methodology to prevent and mitigate losses from this phenomenon. Scale inhibitors are chemical reagents used to prevent the nucleation and growth of scale crystals, and most scale inhibitors use monoethylene glycol as a solvent. In this study, ANSYS Fluent is used to perform the three-dimensional numerical simulation of the two-phase, two-component laminar and transient fluid flow from the injection of monoethylene glycol used as a scale inhibitor solvent into the oil-water mixture in a vertical pipeline as a methodology and initial prediction of the mass fraction of this substance in the flow. Simulation of 8 cases of the two-phase and two-component flow of monoethylene glycol into the oil-water mixture in a 50 meters long pipeline was performed. Table 1 shows the physical properties of monoethylene glycol in oil and water. Figure 1 shows the schematic representation of the MEG and oil-water inlet in the pipeline. The injections are performed with constant velocities or according to the transient velocity profile case present in Figure 2. Pipeline cross-sections are considered inhibited from scale formation if they reach the MEG mass fraction shown in Table 2. The multi-phase formulation was performed using the mixture model, which is a simplification of the Eulerian model based on the assumption that the Stokes number is much smaller than 1. In this model, we solve the continuity equation for the mixture, the momentum equation for the mixture, the mixture energy equation, the volume fraction equation for secondary phase. In the species transport model, we solve the mass conservation equation for N-1 species in a mixture. In laminar flows, the diffuse flow is described by equation 6, and the enthalpy transport due to species diffusion is described by equation 7. The MEG mass fraction were analyzed at different flow times for the transient and constant injection cases. At constant velocity, the values of the predicted average profile of this mass fraction are somewhat lower than the values obtained for the transient injection velocities. it is possible to verify that the flow reaches the steady state from 60 seconds. In all cases, it is observed that the average mass fraction is always higher than or equal to the required mass fraction from this T value. These figures show color maps of the pipeline cross-section and longitudinal section for case 1, with transient injection velocities and constant injection velocities. It is possible to analyze how the diffusion of monoethylene glycol occurs in pipeline, always having a more significant amount of the substance on the same side where the injection is performed. Figure A shows the prediction of the mass fraction for case 4, transient injection velocity, using the reference mesh. With the reference mesh, a minor mass fraction was predicted than the initial solution for the MEG inlet. At the pipeline outlet, the initial and the reference solutions converge and predict that from t equal 15 seconds, there is MEG at this location. From the results obtained, it was possible to verify that from t equal 60 seconds, the flow reaches the steady state and the average mass fraction is always greater than or equal to that required mass fraction. The color maps found that the pipeline is partially inhibited even in cases where the average fraction is higher than the required mass fraction. The reference solution predicts a lower mass fraction than the amount predicted in the initial solution at pipeline inlet, and both solutions show that 15 seconds of injection are required for the monoethylene glycol to reach the pipeline outlet. The modeling presented an initial methodology to evaluate the diffusion efficiency of this substance acting as scale inhibitor solvent in oil pipelines, and to validate this strategy, other studies in real scenarios are needed. More numerical experiments will be conducted in which turbulence effects will be included and dynamic mesh adaptivity will be used. Thank you for your attention.